So I'm going to get started on the last of the statistics and machine learning lectures. So yesterday we had spoken about the Niemann construction for making confidence intervals, and that is a somewhat involved technique. One thing that you can do instead, though, is use Wilks' theorem. So the idea with Wilks' theorem is that the negative log likelihood, or the negative 2 log likelihood, is asymptotically Gaussian. But what we mean by that is that you essentially get, it tends towards the chi-squared, basically, as you collect more statistics. And so you can use this by saying that if you do your fit, and find your best fit point, right? And then you map out what your negative 2 likelihood surface is relative to that. The delta between any given point and your best fit point should follow a chi-squared distribution with k degrees of freedom, where k is the difference in the number of free parameters between those two fits. So now, to give an idea of what that means, right, let's say you have a 2D surface, right? When you do your best fit, you get that. So imagine you have 100 parameters in your fit. That's a lot of parameters, but you do 100 parameters and you do a fit, and you get some best fit and you get some negative 2 log likelihood there. You then basically evaluate on a grid around it on 2 parameters of interest, right? So this is parameter x and parameter y. So at each of those grid points, you hold those 2 parameters of interest, x and y, to the value of that bin. So actually, all those fits only have 98 free parameters, right? So when you take the difference between the negative 2 log likelihood between one of these points on the grid and your best fit, there's 2 degrees of freedom left over, right? So that quantity should obey a chi-squared distribution with 2 degrees of freedom, right? So whenever you're making, so if you wanted to make a 1D distribution, right, where you had sort of your variable here and your chi-squared value there, right, like this, in this case, you would use a chi-squared of 1 degree of freedom, right? The difference between here and here is 1 degree of freedom. If you're trying to make a 2D surface where you're trying to figure out a 2-dimensional interval, you'd be using 2 degrees of freedom, and so on. You don't do much more than that usually because it's too difficult to do, 3D histograms and fill them in, but it's in principle possible. So this difference is what we use to set the interval, and the size of the difference that you go up is a critical value, though colloquially people call it the up value, because it's how far you go up from the minimum, right? And because this is chi-squared distributed, at least asymptotically, the way you get these numbers is essentially just by taking the integral, the tail integral of the chi-squared function, the chi-squared distribution. This is important enough that tables have been tabulated for this, right? So this is from the particle data group statistics review, which is something that you should probably just download and have on your computer at all times, because it's a great place to just look up stuff if you forget. But the idea is if you want to do a 1 sigma interval, then if you have 1 degree of freedom, then your up value is just 1. You just go up by 1 unit of negative 2 log likelihood, and then as you go up, it goes to 2.3 and then 3.53. So, and then as you go to larger significances, the up values are bigger. Now, also, you don't even have to use the table. There's a function in root, which is to basically doing this integral for you. So if you do chi-squared quantile, the confidence level that you're targeting, and then the number of degrees of freedom, it just tells you what that up value is. So in a lot of my macros, I just, the confidence level contour that you want is just a free parameter that you give to your program, and it calculates what the right up value is internally. So again, like I said, you do this whole idea of making a grid, a surface, a chi-squared surface, people often call it, when you're constructing these things. So many of the plots you see like this where you see a limit placed, those limits were at least initially set using Wilks' theorem, right? Though I will say that Wilks' theorem does have some notable problems. It's only true asymptotically. Like many things in statistics, we have asymptotic guarantees that are very likely not held up at any sort of finite statistics, especially not neutrino experiment types of finite statistics. So if you think you need a Poisson likelihood, then Wilks' theorem is probably going to be at best an approximation. The other thing is that it's not valid if the true value is on the boundary of the parameter space. And actually, this story is a little bit more complicated. Anytime you have a parameter space where the results do not change monotonically with the parameter, right? So think about an oscillation, like a mixing angle, right? When you're near the center of your distribution and you change the mixing angle, your prediction goes up or goes down. As you reach the edge of the range of the parameter, that starts to turn over again, right? Like as you approach maximal mixing and then go past it, your prediction gets bigger and then gets smaller again. At that boundary where you have that turnover, you reach a point where your prediction can't actually get higher than any particular value, right? You've reached a boundary in how many events you can actually wind up predicting. And when that happens, you don't expect the likelihood distribution to be a Gaussian anymore, right? Because if you think of these errors, these confidence intervals as being like an ellipse, as you get to a region where things compress, the ellipse gets sort of stuck and morphed around the edges. So those are places where Wilks' theorem doesn't hold, and any time where you have small signals, or again, like an oscillatory parameter space. So in neutrino physics, most things are oscillatory, and those are precisely the types of places where Wilks' theorem has trouble, right? Where it will not be true. The other thing that I mentioned briefly yesterday was that well, no, that's not with Wilks' theorem. So Wilks' theorem can have a problem because of these, where there'll be distortions. And if you want to do better than Wilks' theorem, you basically have to use Monte Carlo methods, right? So instead of integrating a PDF, you have to empirically determine the PDF in order to set your confidence intervals. So there's a couple of different, actually there's many different ways of doing this, but there's a handful that are in sort of common practice. One of them that's very common, especially in neutrino physics, is called Feldman-Cousins. So it's called that because Gary Feldman and Bob Cousins came up with it when they were trying to figure out basically how you would set limits at, I think it was Nomad, actually, where they expected not very many events, right, to see. And the basic problem they were trying to deal with was that whenever you have an interval in a frequentist prescription, that interval must cover the appropriate amount, basically whatever the confidence level that you've set it is, that's the number of times, if you redid the procedure many times, and it's a 68% confidence level, the true value should be within 68% of the different intervals that you've made, right? And if that's not true, if fewer or more than that, you either undercover or overcover, and both are actually considered very serious sins from a frequentist perspective, right? Because it's basically your confidence level, your confidence interval does not contain the probability that you claim it does, right? So one of the things that they found is that when we do this Niemann prescription, right, we just said that for a given true value, you sort of figure out all the different observations you can make, and you take like a 68%, an interval that contains 68% of the outcomes in it. What I didn't say then is that that prescription is actually a little ambiguous. Because if you imagine your probability distribution, you can start your interval anywhere you want and then just extend the interval out until 68% of the outcomes are in it, right? Oftentimes we think of something called a central interval, which is that it's centered around the most likely value for that, the most likely outcome, and you place an interval symmetrically around it. But you can also have upper limits, right, where you expect to see nothing, and you want to say, see, given that I've seen nothing, how large of an effect could there have been that I would not have seen it yet, right? And those are intervals that are all the way to the edge of the parameter space, like to the smallest effect going up. And so one of the things that they observed was that oftentimes people before Feldman-Cousins would basically say, they'd have some criteria, and they say, if I don't see anything, I'll set an upper limit. If I do see something, I'll set a central limit. And they might come up with, like, if I see between 0 and X number of events, I set a lower limit. If I see more than that, I switch. And what they found is that if you look at what the coverage is of these intervals, there's a flip-flopping that happens when you transition from lower limits to central limits, right? Central intervals. You get this flip-flopping in coverage that actually violates the coverage guarantee that you have. And the primary problem there is that you're making a decision about the type of interval you're making based on the data you've seen. And that is the problem. So they came up with a thing that they called a unified method. So it's like something that works always, regardless of whether or not you're setting, regardless of what type of limit you're setting. And the idea is that the method actually smoothly transitions from one type of limit to the other without having to depend on your data. It's actually being based on what the pseudo experiments say you should be doing at each of these different regions. So the basic idea is to use an ordering principle, right? So like I said, there's ambiguity about which part of the probability distribution you select. So this idea is you have an ordering principle which tells you which things go inside your interval. And the idea is that you basically make a difference in -2 log likelihoods between an evaluation at what the bin, let me put it this way. You basically make a surface. At a given bin, you basically draw pseudo experiments at that bin point. So you know what the true values are because you've picked a point in your parameter space. You evaluate your -2 likelihood plugging in the values that you know are true, right? Then you do a best fit, you let the parameters float, and you do it again. The difference in those two values is your likelihood ratio that you use to order your outcomes. So you may build this many times to make a probability distribution of this -2 log likelihood ratio metric, a figure of merit. And then you determine, like let's say you want to set a 90% confidence level limit, then you find there's 90% of the pseudo experiments live inside here, and then you find the value of your -2 log likelihood ratio that contains those 90%, and that's your critical value or your up value. So in each bin, you then compute this figure of merit when you have your data. That tells you your observation, and you use that compared to your critical value to determine whether or not that bin is inside your interval. And what we find is that we get some reasonably large changes in our distributions, in our contours. So this is in NOVA, and it shows basically if you have no Feldman-Cousins, it's the dashed line, and with Feldman-Cousins, it's the black line. So you have places where your significance actually goes down and places where your significance goes up, right? So it can make the interval larger, and it can also make the interval smaller, depending on the details of the parameter space at those points. And this gives you exact coverage guarantees as long as there are no nuisance parameters. Just so you know, nuisance parameters are basically parameters that are not of interest, right? So when in this plot, delta m squared 3,2 and sine squared theta 2,3 are your parameters of interest, everything else that you're not showing here is a nuisance parameter. Whether it's a physics parameter or a systematic uncertainty, if it's not on that plot, it's a nuisance parameter, right? And so if you have a model that has more parameters than you're actually showing, then there are some details that can make the coverage guarantees go away. And that mostly comes from needing to figure out what ensemble you're generating over in terms of what values are you sampling from for your nuisance parameters when you're generating your pseudo experiments for this. Yeah, so this is an incredibly time-consuming method, and largely it's because of the best fit. So at every point, you have to generate many fake experiments. You have to evaluate your likelihood at that point, and then also a best fit, where your parameters of interest are free in the fit there. And that best fit is often very time-consuming. So if you have something like the atmospheric mass splitting, right, in your fits, that's often something that takes time to let Minui scan over and find the best fit for that. In terms of the coverage guarantees, for things like discrete parameters, like the mass ordering, this is particularly challenging to deal with and getting it right. So NOVA has explored ways to improve the coverage, and there's an archive article that is worth reading. I think it's really good, but it's still controversial. Like, this is something that within the community, there's not an agreement on how to do it. So it's sort of, this is not a settled subject, right? This is sort of at the edge of what people sort of like have agreement on about the correct way to do this. But these sorts of things are very important. So there's been a lot of discussion in the past of things like dealing with sterile neutrino results, right? Especially the different things like prospected neutrino 4 and all of those experiments where there were mostly negative results, but a couple of unusual positive results. And there were some papers out that basically showed that, you know, a lot of this might just be due to inappropriately using Wilks' theorem, right? And that if you properly Feldman-Cousins all of these, you don't see the sorts of effects that are claimed. So these sorts of things should be checked, especially when you're making an extraordinary claim. Now, one other frequentist-ish method, it's frequentist, but it's not completely it's not necessarily based in foundations exactly the same way as some of these other methods are, is called CLS. This is trying to solve a problem. So when we knew our normal discovery significance, right, we use a standard p-value approach, and you basically say, what is the probability of finding a more extreme result than you actually got, assuming the null hypothesis? And sometimes you'll find that that p-value you get is extremely small, which means that you get a high significance, right, result. But what if you just have a bad fit and none of your hypotheses are good, right? Let's say you're doing a sterile neutrino analysis and you fit using the three-flavor hypothesis and you get a very small p-value. So you say, I can reject that. But what if you try every single sterile hypothesis and they're also bad fits? Then it's not a good idea to claim that you've discovered sterile neutrinos just because your standard model is a bad fit. You've just discovered that everything is bad, right? So this idea is saying that you should not exclude points in parameter space that you don't have any sensitivity to, right? So if you actually are not sensitive to a given alternative hypothesis, you should not be excluding that point. You should treat that point more as a place where you don't know why you're bad, but you're bad at this. You're bad at fitting anything in that point, right? And maybe this is something that you need to dig into deeper, but you shouldn't make claims about a particular model. So you formulate a new metric, this -2 log Q, which is essentially another likelihood ratio where this is -2 log likelihood of your data given that hypothesis 1 is true, your alternate hypothesis, and then minus -2 log likelihood of your data given your null hypothesis is true. I'll note these theta hat and theta hat hat just means that is the best fit, right? So theta hat is the best fit of your parameters under H1, and theta hat hat is the best fit parameters under hypothesis H naught. I made a mode modification to my slides because it's something someone asked me. If you have systematic uncertainties, it's not enough to have the systematic uncertainties as poles in your fit. When you do this method, we're going to generate fake experiments. You have to fluctuate your systematic uncertainties in the generation of the experiments in addition to in your fit in order for the method to work sort of as advertised. So what you do is you want to find out the distribution of this metric under H0 and under H1. So the idea is you generate a series of fake experiments. You generate null hypothesis fake experiments and alternative hypothesis fake experiments. Each time you generate one of these fake experiments, you fit it twice. So you fit where H0 is true, you fit it assuming H0 is true and assuming that H1 is true. And then where H1 is true, you fit it assuming H0 is true and where H1 is true. And so you construct from that two different probability distributions. The probability distribution of this metric under the case where H0 is really true, and the distribution where H1 is really true. And these are these two different distributions here. So the black here is your null hypothesis probability distribution, and the blue is your alternative hypothesis distribution. And what we do then is we compute CL1 minus CLB, or you can actually think of it as CLB, which is your normal discovery p-value here, right? So it's CLB is basically the confidence level p-value if the background only hypothesis is true, right? And then you compute CLS plus B, which is the confidence level of the signal plus background hypothesis. And that's this bit right here. Let me pick a different color that shows up a little bit better. Right? That doesn't actually show up any better, but I think that's the best I can do. So you have these two different p-values. The first p-value, the 1 minus CLS, so the CLB, right? So this pink area is your normal discovery p-value, right? So if normally you would say if that is small, then you would reject the null hypothesis. This other one, this CLS plus B, is a measure of sensitivity. The bigger that is, the more sensitive you are to the alternate hypothesis that you're looking for. And then you construct a thing called CLS, which is the confidence in the signal only, which is the CLS plus B divided by CLB. And the idea here is that you exclude a point at alpha confidence level if CLS is less than 1 minus alpha. Okay? So again, this is like if you have a place where you have a very small discovery p-value, but your sensitivity is tiny, it's saying that you should not exclude that point because for instance, if this was a sterile analysis search, if you're in a particular bin where your sterile parameters, you have no sensitivity to those sterile parameters, it doesn't make sense to exclude that point. Okay, now let's move on to machine learning. So when we talked about the Neiman-Pearson lemma, we said that the highest power classifier is defined by the behavior of a likelihood ratio, right? So the probability distribution of a test statistic under your null hypothesis and under your alternate hypothesis. So it's possible often to build multidimensional likelihoods empirically, basically making multidimensional histograms under these different hypotheses to construct this. To allow you to construct this decision surface of basically of what is one thing versus the other. But if you have more than like 3 features, this becomes very untenable, right? Because you have this cursive dimensionality, right? The number of bins in a histogram increases a lot as you increase the number of variables that are inside a histogram, which is a problem because of memory. And it's also a problem because the amount of Monte Carlo statistics you have to generate so that every bin has enough events in it that you can estimate the probability distribution, probability in that bin becomes impossible. You can sometimes make a series of 1D likelihoods and then stitch them together, but then you lose all the potential power that's due to the correlations between features. So you need a way to generate an optimal test statistic that can model nonlinear relationships. And this fundamentally is the reason why people invented a lot of machine learning techniques. So the neural network, artificial neural network, which its name is the multi-layer perceptron, is one of the first things people came up with. This dates back to 1958. And the idea was to try to create a computational algorithm that could approximate generic functions, right? You could arbitrarily well approximate a function. And this process can be used to learn a test statistic. So if you've ever made a selector where you put in input features and then you try to train it so that the function yields 1 if your signal and 0 if your background, you have made a test statistic. That's what you're doing when you do that. So what's actually happening here is that multi-layer perceptrons have layers of different nodes. And the idea is that each node performs a transformation on a weighted sum of inputs from the previous layer. So you have a previous layer sends numbers to a node which aggregates all of those incoming features, and then it applies a nonlinear transformation on it. And then it in turn passes it on to the next layer. So basically it simplifies things. So every node in layer L-1 is connected to every node in layer L, but not connected to layer L+1. And then you pick the best weights. So on these nodes, you have like weight 0, 0, weight 0, 1, and so on, right? You have some sort of technique to iteratively refine those weights in order to make the outputs match your desired function to the accuracy you need. So this is just a simplified example just to see what the calculation means. So you don't usually do just 2 layers. You usually have at least 1 hidden layer. So you have an input layer and an output layer, and you have at least 1 layer of hidden nodes in between. But what you're doing is you have these weights. You basically have a matrix of weights, right, that tell you how to transfer data from one layer to the next layer. And then, so like this Y1 node aggregates everything from X1, X2, and X3 weighted by these weights. So it's just a linear sum of the inputs. But then you push it through a nonlinear function, sigma. And commonly, this is the sigmoid function. So 1 over 1 plus e to the minus x. So the idea is that this is approximately linear around 0, and that it's highly nonlinear when you go to larger values. And then eventually it saturates at the edges. And this is used to try to model the way we think neurons work, right? A neuron, you have each neuron has like one, axon coming out, and you have dendrites coming in. And so it's receiving signals from other neurons. And when those signals reach a certain threshold, the neuron fires and sends a signal out, which then connects to other neurons, right? So strictly speaking, biologically inspired neural networks should use step functions, but we use sigmoids because sigmoids are differentiable and step functions are not, which, as we'll see, is important for actually training these things. Now, you need some way of determining whether or not your neural network is doing a good job, and so we use something called the loss function. This is basically a likelihood, right? So it's some function which compares the truth for some data fed into the network with predictions about that data, right? And so if the predictions and the truth match each other well, the loss is small, and if they don't match, the loss is big. Exactly what you mean by matching depends on precisely what the loss is. If you're trying to classify things in a binary way, signal background, then the loss that's usually used is this one, called the binary cross entropy. This is very closely related to just a binomial probability likelihood. But if you were doing things like you wanted to figure out distances, you might use something like the Euclidean distance as a metric, which would be the L2 loss, or an L1 loss, which is basically the absolute value between the 2 different positions. Training, your loss function is a super high dimensional surface, right? So the dimensionality of the surface is the number of weights. Networks often have millions of weights in them, so this is a millions of dimensional surface. You want to know how to walk down this surface to the minimum point in it. You're trying to minimize your loss. And so what you want is your gradient, right? If you compute the gradient of the loss with respect to all of your weights, that tells you the direction of steepest descent. Well, minus that is the direction of steepest descent. So we do something iteratively. You start off with some random point on your loss surface. You compute your gradient at that point. You take a small step along that direction of the gradient. Because you're nonlinear, you can't just go all the way down to the bottom, but you take a small step, then you recompute it, change course, and go again. So this process is the gradient descent algorithm. If you do it over mini batches, so basically you take like 32 examples of training data. You compute the gradient relative to that and then go. Then you put that data aside and take a new batch of 32. So each time you're doing this, it's actually a new loss surface that you're looking at. Then the statistical noise from the fact that you're using fewer events in the computation of your loss means that different minima and maxima open up randomly in your surface. So you can be going down a direction one way, and then the noise bumps you out of that and derails you. You would think that that would be bad, but it turns out that the loss functions that we actually have many, many minima, right? So I mentioned before that there's no one single way, there's no guaranteed way to find the best minimum when you have a surface with multiple minima, right? The idea with using stochastic gradient descent is that the noise tends to bump you out of low significance minima, so that as you random walk around this surface following these noisy gradients, you tend to fall into the largest possible minimum, because smaller minima tend to appear and disappear because of the noise. So this is a case where the noise in the learning process is actually a useful thing. And then this eta is the step size. It's how big of a step you take when you take along the minus the direction of the gradient. And that is a hyperparameter. It's something that the algorithm doesn't specify what the right size is. That's something you have to actually test different values to see how well you learn. If it's too big, you just jump over features. If it's too small, you never get anywhere. So you need to sort of play around with it and see what sort of value makes the training progress in an optimal way. Now, also, you have issues with overtraining. So what you're trying to learn here when you're learning a classifier is you're learning a decision surface, right? You're trying to figure out which examples are inside your surface and which ones are outside your surface, right? So this is sort of showing you're trying to separate red from blue, and you could make a nice smooth decision surface, which will misclassify some things. Or you could make a very complicated decision surface, which will perfectly carve out every example of blue and red. The argument that's made is that it's better to have the smoother surface, that you should penalize overly complicated surfaces. And the reason why is that you're training on a finite set of training data. And if you make a very complicated surface, then you've tuned your decision surface to perfectly match the input training data that you've used. But any statistically independent set of data is likely to not have those exact same fluctuations. And so you will have made a surface that's over-specialized, right? It's too good at that one training set at the expense of being bad at every other set, right? So we tend to try to penalize it. We put an L2 regularization term to penalize overly complicated arrays of weights. And so it penalizes the complexity of the decision surface. Now, all this being said, the question is, why is this not good enough? Because these came up in the 50s, they were very briefly popular in the 80s, and then neural networks died as a field until 2012, right? The reason why is that even though you can theoretically prove that a neural network, even a single layer neural network, is arbitrarily good at approximating any well-behaved function, actually making a real instantiation of a network that can do that is very hard, right? So in principle, you can do it. It might take infinite nodes, but mathematically, it should work. You can always approximate things in a piecewise way with these nonlinear functions. But in practice, it doesn't really work, right? So the networks become very difficult to train, and the performance was generally just disappointing, right? Despite the theoretical guarantees, in practice, it just didn't work. So, and then the other part of this is that these networks are fully connected, which means there's a lot of free parameters, right? You add more layers and the number of free parameters explodes, and which tends to increase overtraining, because the more weights you have, the more complex of a decision surface you can build out of those weights. So you tended to, if you made it powerful enough to do what you wanted to do, it tended to overtrain, and otherwise it wasn't powerful enough and you didn't have a very good result. And so people were generally pretty disappointed. In the 90s, decision trees became extremely popular. So decision tree is a pretty straightforward idea. It's basically just the algorithmization of what we do when we make cuts, right? If you do a cut-based analysis, you look at the distribution and you say, my signal's mostly over here, my background's mostly over here, I'm going to put a cut here. And then applying that cut, you look at another parameter and do the same thing. And you just keep applying cuts, boosting the purity of your sample through successive cuts. The idea here is that you basically come up with a series of features, which are like reconstructed variables, which separate signal and background to some degree. And these decision tree algorithms will basically randomly select from this bag of features, and it will optimize the information gain, right? It'll find the value of the cut that optimizes the information gain. And then once it's done that split, it picks a new variable, and it does the same thing over again. And it keeps doing that recursively until you cease getting any more information gain, or you've reached your predetermined limit on how deep you're allowing your tree to become. Right, and so this is a decision tree. The nice thing about these are human understandable. You can basically print out the decision tree the algorithm made and see if it makes any sense. So these are effectively making a series of hyperplane decision surfaces. You have a space and you're just making planes through the space. These are invariant under scale changes. They can handle discrete inputs, and it's robust against outliers. But the con here is the performance is incredibly weak, right? So they're only a little bit better than random separation. And also, if decision trees become too deep, which tends to make the classification better, they then overtrain, right? Which is why you tend to put a limit on how deep you're willing to make a tree go. So again, these were, people knew about decision trees. People have been making these just manually for a long, long time. But one of the questions that came after people were moving away from neural networks is, can you make these better? So people came up with this idea of boosting, which is a generalized technique for taking weak learners and making them strong learners, right? So the idea is you generate a random tree. You basically use your algorithm to generate a decision tree. And then you classify all of your training data with that decision tree. And what you say is, anything that it classified correctly, it's doing a good job on, you don't need to do anything else with. But the stuff that it failed at is doing a bad job. So you assign a weight to every event, where you downweight events that are classified correctly, upweight events that are classified incorrectly. Then you generate a new random tree based on that new weighted data, right? Where the information gain is now modified based on those weights. Then you take those two trees and you classify based on the average output of those two trees, right? So this is just like a voting issue. The two trees vote on whether or not an event is in or out. And so you take the combination of those two trees and then do the reweighting again, right? And you keep doing this, building new trees based on a boost factor from the aggregate of all the previous trees. And as you keep making new trees, each individual tree is weak, but the ensemble of trees is very strong. So the idea is each of these trees is sort of tuned for one chunk of your parameter space for doing a decision there. So that lets you optimize on different populations of examples. BDTs tend to work extremely well when operating on a relatively small list of reconstructed features. Right, so anytime you have a handful of features that you want to try to make a classifier for, a BDT is almost always the thing you should try. They almost always work best. So this is an example from Atlas. These are still in wide use now. They tend to be resistant to pathologies due to including irrelevant features. So if you put a feature in to your training that just doesn't work very well, the algorithm just tends to ignore it, and it doesn't bother anything. And this became the gold standard for quite a long time. And if we think about why this is, multi-layer perceptrons are arbitrarily powerful, and yet they do a bad job. BDTs are in fact a collection of incredibly weak elements, but they do a very good job. And so how can you make sense of that? Well, MLPs can only work if you can successfully train it, right? You have an algorithm which has sort of infinite potential, but you then have to instantiate an actual network that can do the job you want. And finding the network that actually does the job out of this space of infinite potential is hard. It's picking a needle out of a haystack, right, of a network that does exactly what you want it to do. Whereas BDTs actually essentially do the same thing we would normally do. We pick features which tend to separate different types of events from each other. BDTs just do that, where instead of making just hyperplane decisions, it makes piecewise linear hyperplane decisions, right? So it sort of makes a finer boundary around it. Each one of your trees in your decision tree basically takes your hyperplanes and then makes a new sort of like a piecewise linear version of the hyperplane instead. So it's just a more complicated way of doing something that we intuitively do anyway. And so the lesson here is that in matching the inductive bias of a given problem is very helpful. And what I mean by inductive bias is that if you have some understanding of the nature of the problem and you build something which matches the structure of the algorithm actually matches the structure of the problem itself, it tends to train much better and perform much better than having an infinitely flexible algorithm does, right? So that's, in some ways you can think about this as like, people often talk about when a baby is born, it has more neurons than you have now, but obviously you're smarter than a baby. Because part of what happens of learning is, pruning. You're selectively pruning out irrelevant connections, which limits potential, but also improves ability to actually do tasks, right? So sort of like pruning into making a more limited but better algorithm is useful. So this then moves to the idea of deep learning, which is sort of the revolution that renewed interest in neural networks. The idea here is, what if you want to have an algorithm that works on relatively low-level features? So BDTs work great when you have a handful of high-level features, right? Like you have an reconstruction algorithm that tells you things like reconstructed energies, reconstructed momentum, things like impact parameters, things like that. But what if you want to work on like hits in a track itself? BDTs can't typically handle features like that. The idea was to attempt to build an extractor which can build high-level features out of low-level inputs. So you would sort of have something that pulls out progressively more complex features going on. So convolutional neural networks were the thing that sort of started this out. It's inspired by studies of the visual cortex in cats. Actually, the idea is that the visual cortex has receptive fields, right? So the neurons in your retina connect, ones that are geographically close to each other are connected to things called simple cells, which aggregate the information from small patches on your eye. And those go through successive layers which have cells which aggregate the simple cells, right? So you get progressively larger fields. And then you have other cells, which are complex cells, which are activated when you have which activation doesn't, if you have a pattern, if you sort of show a pattern to a cat and sweep the pattern across its eye, the activation pattern doesn't change as it moves. So it's sensitive to a pattern, but it doesn't care where the pattern is, right? So there's sort of things that are translation invariant, and there are things that are interested in local features. And this sort of fits the idea of a natural image. Natural images are information dense, right? Like if you want to interpret one little bit of an image, the stuff immediately around it is very important. Whereas the stuff on the other side of the image is not necessarily as important, as relevant to that piece over here. So the idea was these cells could be modeled as applying convolutional kernels to the inputs. So a convolutional kernel is just it's a discrete transform where you have essentially a matrix of weights, and you take the dot product of that matrix of weights with a grid of pixels, and then take the output and put it into a new image, right? And so there are many convolutional kernels that are known, and they do specific things. There are edge detectors, which essentially find when the derivative of an image changes abruptly, and there are blurring ones, and there are sharpening kernels. If you've ever used Photoshop, basically every single tool in Photoshop is applying a particular convolutional kernel to your image. So the idea is that these convolutional kernels extract features from the image. The question is, could you actually make these kernels learned? Rather than using a set of predefined kernels, could the algorithm learn them themselves? So the idea is to have this idea of convolutional layers where the weights in your neural network are actually the kernels that are being applied to your image. So you have maybe a 3x3 grid of weights, that you learn, and then you sweep it across the whole image. You translate it across the image and compute the convolution of that kernel with the image itself to produce a derived feature map. So you have an input feature map and then a derived feature map. And then you basically have layers successively which refine this. So you basically apply another convolutional kernel to your derived map to make another derived map to make progressively higher level features. You can also have pooling, where you basically take a downsampling of grids. So you basically apply a little grid, and either you take the highest value, the most significant information in the grid, and pass it on, or you take the average of all of it. This can be thought of like a smoothing operation, and it applies some degree of equivariance to translations. So the idea being that if you move something around in your image, it doesn't change the response of the network to the existence of that within the image. Okay, so NOVA was the first experiment to have one of these. We called it the convolutional visual network. The idea is that we have inputs which look very much like images, which are just our events looked from the side and from the top. We put them through two parallel convolutional neural networks, and then once the features become very abstract, we merge them together and make a final decision about what type of neutrino it is. And we find that it does very, very well. Now, I should say quickly that whenever you see grids like these are called confusion matrices. They're a summary of the performance of a network. They can display either efficiency, which is the fraction of true samples which are correctly selected, or the fraction of purity, the fraction of selected samples that are actually correct, right? Which are different things. These are both efficiency. So the idea here is if you select a neutral current event, then 89% of 89% of true neutral current events are selected as neutral current events, right? In this algorithm. You can also use different ways to sort of probe the behavior. So like decision trees, you could actually inspect an individual decision tree. You can't inspect neural networks in general, especially not really deep ones. But you can use things something like t-SNE, which is like called the t-distributed stochastic neighbor embedding. This is a technique for taking the final layer of your network, which may be very high dimensional. So in NOVA case, it's a 1024 dimensional output. And basically trying to make a two-dimensional representation of it that preserves similarity. So the idea is that examples that are close together in 2 dimensions are close together in similarity in the high dimension, right? So you have a metric of similarity that you compute in high dimensions, and then you map that to physical distances in 2 dimensions. And you can basically look at how things cluster to try to get an idea of what types of features the network is using to make decisions. So we did this, and basically these different colors are different types of events. So the NUIs are almost all down here. Like the new Mus are over here mostly. But what you can see if you look at examples is that to the right-hand side are events that are dominated by tracks. The left-hand side is a side that things that are dominated by showers. Moving to the upper corner, you're dominated by hadronic showers. The lower corner, you're dominated by electromagnetic showers. And then on the other side, you're dominated by either beam-directed tracks or steep angle tracks, right? So part of this is you can see that like the steep angle tracks is when you start becoming more ambiguous with cosmic rays, right? So these are the new Mus where you're not 100% sure anymore whether it's a new Mu or a cosmic ray. So these types of analyses can help you get an intuitive understanding of what it is you're looking at. You can also do occlusion tests where you basically remove some pixels from your event that you're classifying, and you see how it changes. And this also gave some very intuitive things. So this is a neutral current event, and we have a pion here. And what we found is that if you cover up these little bits over here, where it's acting particularly pion-like, suddenly it's not quite sure if it's a muon, right? And so if you cover up these little bits where there's nuclear interactions happening, suddenly it says, well, this might actually be a muon. And it changes its decision from neutral current muon neutrino. Similarly, if you have a true electron neutrino, electrons are electromagnetic showers. The only real difference between an electron and a photon is how long it takes for it to start to show up in your detector. Photons travel visibly for some period of time until they pair produce for the first time. And once they pair produce, they start ionizing and causing your scintillator to light up. So if you cover up the very beginning of the electron shower, all of a sudden this says, I actually think this might be a photon. And if there's no electron in here anymore, it's probably not an electron neutrino, it's probably a neutral current. Right? So this is actually exactly how a person would do it, right? If you were hand scanning, this is how you would make the same decision, essentially. So this was very encouraging for trying to understand how exactly these decisions were made. Now, I'm just going to quickly go over one other sort of option besides convolutional neural networks. There's also operations on graphs. So there's a whole field of geometrical learning that's actually pretty big right now. And this is trying to do machine learning on generalized geometrical objects. So there's like graph neural networks. There's actually things on groups and on manifolds as well that all are attempting to sort of like figure out how to learn on sort of more generic surfaces than just a two-dimensional grid. So the idea with a graph is that your nodes represent objects and your edges represent binary relationships. Right, so this thing here is basically a graph of Wikipedia editors who primarily edit in one language, but sometimes edit in another. And there's interesting behaviors here where English is in the middle because many, many people know English. And so even if your native language is in English, you may still edit English Wikipedia, but it's actually very unlikely that it goes the other direction. Right, and you have some language groups where people tend to speak those languages. And so you see tight connections between some languages, but no connections between others, right? Where it's very unlikely where a person will speak both of those languages. The idea of using graphs for physics data is that they're naturally sparse. The hits have a causal structure that can be modeled by edges. So like if two hits are caused by the same particle, those are related to each other, but if they're not caused by the same particle, then they're not related to each other. And also they accommodate relationships beyond nearest neighbor. So the idea with this is to generalize the idea of a convolutional neural network. So instead of doing convolutional operators on adjacent pixels, you're doing convolutions over adjacency defined by an adjacency matrix of a graph instead. So it's like whatever the edges tell you is adjacent is what's adjacent. And so you aggregate over the edges and then update things. This was used to pretty great effect by Exatrix to try to find tracks in the Large Hadron Collider. It basically is an iterative network where it does operations on edges and then operations on nodes until eventually it upweights edges that are real and downweights edges that are false, and essentially a cloud of tracks emerges from your initial graph. You can also use this for semantic segmentation, which is if you have hits in your detector and you want to know what type of particle created each hit, you can do that. So this is something my group was involved in, which is basically a graph in neutrino interactions, which is attempting to classify hits as being from minimizing particles, highly ionizing particles, electromagnetic showers, Michel electrons, or diffuse activity. And the basic idea is you make some initial graph, which is some initial structure, and then you use something called message passing, where you're doing convolutions over adjacent hits iteratively, and then refining your edges. You're changing the weights of your edges so that they get weighted up if the information is relevant, and they're weighted down if the information is not relevant. And so it dynamically learns what information inside this graph is important. So you can look at this later if you want. There's a complicated structure to deal with the fact that in liquid argon, we have 3 planes of information, that two-dimensional planes, but those are all connected to each other in 3D, right? So we have a structure which does message passing in 2 dimensions and then aggregates that information through 3-dimensional adjacency as well. And so you're trying to make decisions which is consistent in 2 dimensions and also in 3 dimensions. And so it has a message passing strategy that does that. And so this just sort of tries to illustrate it. You have 3 separate graphs. You do a convolution of the node features to the edges to figure out your edge features. You then derive edge weights from the features that you've just made. Then you pass across those edges in a weighted way to make new features on your nodes. Then you propagate those up to your 3D nodes to aggregate from the 3 different views. You do a convolution of those features in the 3D nodes to generate new high-level features. And then you propagate it back down to your 2-dimensional planes. And so by doing this, you're sort of learning inside the planes, mixing the information between planes, and then propagating it back down again. And in general, this worked extremely well. The overall efficiency and purity was about 95% across all the different categories. And the consistency between the planes was very high at 98%. And just to look at what some of these things look like, you can sort of look, this is a truth event display where you can see sort of electromagnetic showers and also tracks. And then if you look at it after we prediction, you get almost everything is right. Only a few hits are misclassified. Okay, now the very last thing I'll talk about is some future ideas. So something that I'm particularly interested in that we don't know how to do yet, but we're trying to figure out how to do, is essentially to use things like these graph neural networks to do complete end-to-end reconstruction. So the idea is, can we use 3D information from the start and build a fully differentiable model where you're not making serial decisions? So remember at the very first talk, I talked about how we do clustering in space and time. You find a vertex, you find individual prongs, you create your event that way and make decisions. Every step along that way has inefficiencies, right? If you do your initial space-time clustering and you miscluster, then every step down the way is wrong because of that, right? The errors tend to compound as you go through the serial reconstruction. So what you'd like to do is to sort of do everything all at once, right? Where you're doing every stage of the reconstruction in parallel. And so you're basically making particles, and you're also doing your initial space-time clustering at the same time. So any problems in the clustering feed back down to the clustering in the bottom and fix the clustering, which feeds back up and fixes the particles, right? So the idea is if you do that, you might be able to reconstruct some very complex interactions like tau neutrinos, which we don't have enough of them to afford to get wrong. And so the idea here is you could think of something as like a hierarchical model where you have different notions of reconstruction, things that you would normally consider different stages of reconstruction, as basically different graphs. So you have your physical space, which is sort of the hits in your 2-dimensional plane. Then you have like trajectory segments, which would correspond to the trajectory of a single particle. Then you have whole tracks or showers, which would be like if you stitch together everything that came from a muon traveling or something like that, or all of the little trajectory segments that make up an electron shower, right? Stitching those together, then you can further stitch those together to primary particles. So if you have a charge pions make a track, but then they might decay into a muon, which makes another track, and then decay into an electron, which makes a third track. Those could all be reconstructed separately, but they also have an identity together, right? So you want to bundle them together as well to say these are all, from one perspective, these are all one object. From a different perspective, they're 3 different objects, right? So basically making some sort of geometrical representation which allows you to think about different scales of reconstruction sort of simultaneously. And so there is actually a structure that lets you do this. They're called hierarchical graph neural networks. The idea where you have a multiple scales of graphs, which you allow yourself to do message passing within one scale, and then you have a method for propagating information between scales. And the propagating between scales gives you a way of enforcing consistency across different resolutions of everything. And one of the things that might help with this is that I talked about semantic segmentation, which is like labeling individual hits in your detector. You can also do a task called instance segmentation, which is finding discrete objects, right? So most instance segmentation techniques work on the idea of bounding boxes. So you have an image here, you learn, your algorithm tries to place a box around individual objects in here and then classify what's contained inside the box. And those methods tend to be resource intensive because they basically are making many trials of putting patches of different sizes and finding the patches that have the best response. But they still work reasonably well in natural images, but in a particle detector, you can have objects that sort of intertwine with each other, right? You can have a shower that's coming out and then a track that goes through the middle of it. There's no bounding box that can cover both of them, that can distinguish the two of those from each other. So we'd like to do something else, but the idea is once you have semantic segmentation and instance segmentation, there's also the process of merging those two things together to go from like the identification of an object to the classification of the object based on what's contained in it. And that's often called panoptic segmentation. And there's a reference here you can look at. So there's lots of ways to do this that use masks instead of bounding boxes that work with convolutional neural networks. They tend to work reasonably well, but they struggle with many close together tracks, and they tend to be a little bit fragile. There's also other approaches that we're exploring as well. There's an idea called object condensation, which is an idea sort of using an electrostatic analog where you imagine every hit in your detector, you learn a charge for each of them, and you basically learn a potential where charges that are from the same object in truth feel a force pulling each other together, and ones that are from separate objects feel a repulsive force. And so they tend to want to be separated. And so what this is letting you do is it's basically you're trying to find a placement in some abstract metric space. So you basically imagine like you have your real physical space, and then you're trying to place these hits in some abstract metric space, and you're penalized if hits from different objects are close together, and you're rewarded if hits from the same object are together, right? And so this sort of loss tends to produce a mapping where you can basically draw just like little circles around clusters in that space, and those clusters correspond to particles. So this is something that is being actively pursued at the LHC and that we're working on for neutrino physics. Yeah, so this is just sort of an example of what the potential looks like that you're sort of minimizing. So let me just summarize here. It's very hard to sort of summarize either of the topics of statistics or machine learning because they're kind of almost infinite in scope. Statistics, a lot of it is settled and has been settled for about 100 years, but a lot of it is sort of stuff people are still fighting about right now, right? Basically, almost everything of interest is actually still not settled in terms of like interval setting. There's a couple books that I really loved when I was like doing my PhD that I think might be helpful. So there's Statistical Methods in Experimental Physics by Frederick James, one of the authors of Minuit, and Statistical Data Analysis by Glenn Cohen. They're both really nice. For machine learning, it's a little bit harder to recommend anything because this is a rapidly changing field, right? So neural networks pretty much died out by the 80s. Boosted decision trees were really big in the 90s. And then in 2012, neural networks came back with fury, right, with the deep learning revolution. And as you see on the news, right, like every day people come up with new discoveries on machine learning, right? So it's a rapidly changing field that's very hard to keep up with. I will say that the deep learning book, which you can find online, deeplearningbook.org, or you could buy it, but they have the whole thing online, was written by the people who basically started the deep learning revolution. It's a little out of date now, but it's still a really great place for just understanding how all this stuff works. Also, there's a book, Artificial Intelligence by Henry Physics. Many of the chapters are on the archive, but they're good. It's good from a perspective of like if you want to think about this in terms of physics. So I was involved with one of these that was involved with CNNs and GNNs for image reconstruction. But there's a ton of really nice ones. There's like a boosted decision tree one. There's a graph neural networks for tracking. And there's also some statistical issues in there, like how do you deal with nuisance parameters in general. That's written, it's a kind of a high level, but it's written by Tommaso Dorigo, who's fantastic in statistics. So if you can find those online, they're a pretty good resource. But I'd encourage you to keep, if you just search for a lot of these things online, you'll find tutorials for many of them that are extremely helpful. And I would encourage you to just try digging into some of them because they're, like I said, it's a big and active field. Thanks.
Hi, can you go back to the slide where you are showing the efficiency plot for the CNN?
Yeah.
Yeah. So we have a data sample which is a mix of mu, E, tau, neutral current, and cosmic. And you have more than 90% of efficiency for all of them other than nu tau.
Yes.
So if you are able to separate everything with a 90%, the rest of the sample is nu tau, right? Mostly. So
Not exactly, because the nu tau spread out in everything else. So the problem with tau neutrinos is that an electron neutrino event, the smoking gun is if you see an electron. For a muon neutrino event, if you see a muon, it's a smoking gun. A neutral current is the absence of those, right? A tau can decay leptonically. If it decays in the electron mode, it looks like a nu E. If it decays in the muon mode, it looks like a nu mu. If it decays in the hadronic mode, it looks like a neutral current. And so tau neutrinos just look like everything else. And so if I look at the t-SNE plot, you can sort of see this. So the green are the nu taus. And you can see they're kind of everywhere, right? There's nu taus over in the purple with the nu mu's. There's up there with the neutral currents. They're down here with the nu e's. They're just everywhere, right? Because nu taus, the main characteristic of nu tau is they look like everything else. And they don't look like, there's no one single thing a nu tau looks like. And so that's the basic problem, is that the efficiency is very high, the purity is not as very high, right? So you have to think about the efficiency is what fraction of the truth do I correctly select, right? So I select 90% of neutral currents, I call neutral currents. 10% of them I call something else. But that doesn't mean that sample is 90% pure. There can be other stuff that's in there, right? So if you take instead, you say, what's my selected sample? What fraction of the selected sample is the thing I actually want it to be? That's the purity, right? So the purity and efficiency, your efficiency can be very, very, very high, and the purity can be very low. And actually, that tends to be how it is. The more efficient you are, is the looser your cut you make, right? Which means you're actually less pure because you're letting more stuff in. So it's complicated. Basically, it's complicated. You have stuff that spreads out. So the nu taus, you can't pick a nu tau just by having an anti-cut and everything else, because nu taus are in some sense the contamination for everything else. They're the thing that looks like everything else. They don't look like themselves. That's the fundamental problem. So I will say that I use some old plots. In newer versions, we actually excluded tau neutrinos from this training because they actually just make the training worse. It just confuses the network. It doesn't know what to do with them. So we just exclude them.
So this selection is independent for each flavor, or it's an altogether selection?
It's all together. So the thing that's nice about a lot of these deep learning methods is that rather than using a binary cross entropy, you can use a categorical cross entropy, which is effectively like going from a binomial distribution to a multinomial distribution. And so the idea is you get a score for every category that you train on. And so the idea is that the scores all add up to 1 because they can be interpreted. You attempt to interpret them as a probability. The neural networks tend to be overconfident, so it's not a true probability. But the idea is usually you take the category with the highest probability for a given event is what you call that event. So if you ever read a machine learning paper, they'll talk about top 1 or top 5. Basically, you take all the categories and you say, in top 1, you say, what was the fraction of the time that the highest probability classification was true? Top 5 is when you say, what is the fraction of the time that the true classification was inside the top 5? So that makes more sense if you're doing like image classification where you have 1,000 categories. It might be where like you have a category, like you basically have like a Persian cat and a Siamese cat and like all these different types of cats. And like the network gets wrong what type of cat it is, but it figures out that it's a cat. Like you still give it credit because like it figured out it was a cat, which is pretty good. It may not have figured out the exact particular breed of cat. But so for us, where there's only like 4 or 5 categories, that's less important. We actually want to get it right. Exactly. But yes, so you can have as many categories as you want. We experimented once with actually doing this based on final state as well. Like, so not only did we classify it by the neutrino interaction type, we also classified it based on like how many pions there were, how many protons, and everything like that. It turned out to be just very hard to train. It still basically worked, but it was harder to train when you had like 1,000 different categories. So.
Any other question?
Yeah. Mm-hmm.
So first of all, the energies where the new long-wave kind works, the tau consequently is massless.
Yeah.
So you expect less tau activity.
That's right.
Now I'm asking you that in a dream-like environment, do you have event by event separation for tau-like events, or it is just like I understand that tau will be identified to neutral current.
Right.
Because 66% it goes to hadronic.
Exactly. Yeah.
So when you have like X amount of neutral current event, are you trying to see some excess because tau is also decaying to neutral, to like neutral current event, or it is event by event?
So we want to do event by event.
Yeah, that's
That's what we want. So right now, we did a simple, we did try a convolutional neural network event classifier and got something like a 30% efficiency for event by event selection for tau neutrinos. But that's not quite as good as we would like it to be. And so a lot of the ideas that I have for this idea of the hierarchical graph neural network come from the fact that a tau neutrino, it's not good enough to just know that there is a particular particle in your final state. That's not enough to tell that you have a tau neutrino. Tau neutrinos are the thing that's more that helps you more with tau neutrinos is actually like angular correlations, right? So the particle content and angular correlations are the thing that separates taus from everything else. So there were some people there was like a student who was looking at particular decay modes, and if you do something like the decay mode where the tau decays to a rho, which decays to a charged pion and a neutral pion, you can basically, if you identify 2 showers and you find that it has the neutral pion invariant mass, and then you take the invariant mass of a track with that, and that has the invariant mass of the rho, and then you look at the reconstructed momentum of the rho, and you take the correlation of the reconstructed momentum of the rho with the rest of the hadronic activity in the event, there's like some transverse plane and variables which can separate tau neutrinos. He wasn't actually using any complicated techniques. He was just looking at sort of sequential reconstruction, and he got some pretty decent efficiencies for that one decay mode, right? So one thing you could do is you could look at individual decay modes. Some are harder than others. So like the single pion one is very hard.
But did you simulate this in a situation where you assume all other activities are happening, or it is just like, he's just simulating?
So in the FAR detector, you're only going to have one event at a time.
Yeah, events are
Yeah, so in the near detector, it would be much harder because you have overlapping events. In the FAR detector, you expect to have only just a single event per trigger, basically. So you don't really have to worry about other activity merging on top of it. You just have to worry about the one. So it's sort of the opposite problem from LHC, where LHC you have 1,000 events all on top of each other. With just one, you have a better chance with just one if you can distinguish all the bits from it. So I think that the way to go in the end is if you can actually reconstruct the kinematics of all the constituent parts, then you have a better chance of isolating tau neutrinos than what convolutional neural networks do, which is really looking for just the existence of a type of activity, which is not good enough for tau neutrinos, in general at least.
Okay, since we are running out of time, let us thank Adam for the nice overview in just 3 lectures.